But to start off, we have Mohammed Munna. Munna is a PhD candidate at the School of Environment and Natural Resources at OSU, working under the supervision of Dr. Lal at the Seabase Lal Center for Carbon Management and Sequestration. His research focuses on soil hydrology, soil physical quality, soil carbon dynamics, and sustainable management of long-term no-tillage systems with organic amendments, such as compost and manure and cover cropping. Munna's work aims to enhance soil health and resilience to climate change through improved carbon sequestration and water retention strategies. Let's give a round of applause to Munna.
Good afternoon, everybody. While much of this symposium is based on hydrological modeling, water quality, or watershed scale water challenge, my work looks at the micro scale, the soil itself. Today, I'll present based on long-term organic amendments for plant available water capacity in temperate no-till systems. The world's water, as you know, out of total water, we have salt water 97.3%, while the fresh water 2.7%. And out of this fresh water, we have 69% glacier and permafrost snow, and 30% fresh groundwater, 0.9% others, including soil moisture, 0.3% freshwater lakes and river flows. And my research focuses on the 0.9%, that is soil moisture. Reservoir of available water on Earth. There are so many reservoirs, and again, my focus is on soil moisture, 0.1 million cubic kilometers. It's the reservoir based on which I'm working on. Type of water, it could be blue, green, gray, or black. There is another type of water that is virtual, in between blue and green. Gray or black that can be converted into green with better management. Soil water balance, this equation is helpful to understand how soil moisture could affect the overall water, like evapotranspiration. Evapotranspiration could be explained by precipitation, irrigation, runoff, and change in soil water. And again, we are working on that portion, del S. And deep drainage is also needed to calculate the evapotranspiration. The hypothesis of this chapter is to evaluate the long-term impact of using organic amendments like compost and manures and cover cropping on plant available water capacity under a no-till cropping system in a temperate agro-ecosystem. And the associated hypothesis is long-term application of organic amendments, particularly manure and compost, significantly enhances plant available water capacity by improving mesoporosity and pore structure, especially in the biologically active surface zone, that is 0 to 20 centimeter thick. It's our experimental design. It's completely randomized block design, and it was established in 1997 by Dr. Waterman Lab. We have 4 different treatments: weed fallow, compost, manure, and cover crop. I collected soil sample from 2 different depths, 0 to 20 and 20 to 40 centimeter, and applied herbicide, a mixture of gramoxone and atrazine at a rate of 0.95 liter per acre, and applied cover crop seeds, a mixture of perennial rye, annual rye, red fescue, and bluegrass in the designated plots. Compost and manure were applied with a rate of 15.33 megagram per hectare for compost, and for manure 23.3 megagram per hectare. And those were applied in early April and early December, respectively. As we applied urea fertilizer in cover crop and fallow plots, we had to consider the application of compost and manure with nitrogen bases to keep the nitrogen same or equal for all the treatments. Plant population for corn is 76,000 seeds per hectare, and the tractor and planter we used from John Deere. Penetration resistance was measured using cone penetrometer, soil bulk density using undisturbed soil core, particle density using picnometer, saturated hydraulic conductivity using constant head method, plant available water capacity using pressure plate techniques, and soil organic carbon using CN elemental analyzer. You can see the bar graphs for bulk density, total porosity, and penetration resistance. Compost and manure show significantly lower bulk density compared to other treatments like fallow and cover crop. And similar trend was showed for penetration resistance. On the other hand, the opposite trend showed for the penetration total porosity. For example, manure showed the highest level of total porosity compared to other treatments. The mechanical insights could be organic amendment like compost and manure is very essential to improve soil structure, most importantly in surface layer, and which is also helpful to enhance porosity. Pore size distribution, transmission pores, storage pores, and residual pores, those are very important to consider the plant available water capacity. If we focus on the total storage pore, which is very essential for plant available water capacity, for manure, it shows the highest storage pore percentage compared to other treatments. However, for fallow, it shows the most highest level of storage pore percentage. So what could be the mechanical insights behind that? Fallow soil could have higher storage pore fraction, as we see from this bar graph. You can see here. So it could be like a reflection of compaction, not the soil structural improvement. And manure and compost treatments improved both transmission and storage pores. It created a best balance for pore architecture or network, which is very essential for plant available water capacity. So the bar graph shows the plant available water capacity for different treatments. Again, manure showed the highest plant available water capacity, and the lowest was showed by the cover crop treated soil. Although weedy fallow showed the highest plant available water capacity, this likely resulted from low plant water uptake, as I told you earlier, due to compaction. Soil water retention curve, it's like another term, PF curve. We know it's the logarithmic expression of suction for soil water. It's like the pH that normally we use for water pH or soil pH. From this PF curve, you could see manure showed the highest volumetric water content for both depth 0 to 20 for A and 20 to 40 for B. Irrigation could help to improve the structure, that is mesopore and micropore distribution could be better for that. And as we are applying compost and manure, those could improve to increase the aggregate stability. That's why mesopore and micropore can be increased, which is very essential for retaining more water in soil for plant. Volumetric water content and various suction, we used 9 different suctions to extract water from the soil. So from here you can see this data were used to create the PF curve. And another mechanical insights could be mineral associated organic matter. When we will add more organic matter, microbes would get more foods, which is very essential to get more mineral associated organic matter. That can also influence to improve more soil structure or getting more pore networks in soil. The limitations could be site and soil context, as we considered only one soil types and specific climatic reason. It could vary based on different climatic reason or soil types. The future works could be focused on multi-site and multi-soil validation, linking soil physical quality with ecosystem services, and the application of artificial intelligence and remote sensing. To conclude, I'd say long-term organic amendments like under no-till could improve plant available water capacity. More importantly, for surface layer, menu could provide best balance between water storage and release, and fallow could show the good graphical representation, but that could be due to the compaction or other problematic issues in soil. Those are the references I used throughout these presentations. I'd like to thank to the C-Form sponsors, and thank you so much, the audiences. I'd be happy to hear your reactions or questions. Thank you.
Questions for our speaker?
I know it's soil-centric, so, but if there is any in general questions?
How would soil texture affect the water retaining capabilities?
Yeah, interesting question. The question was like how soil texture could affect the water retention in soil. So as we know, when there would be sandy soil, water wouldn't stay in that soil for a long time. However, when there would be a good proportion of sand, silt, and clay, the soil could store more water. More importantly, when the soil would have more silt and clay, it could be beneficial to create more mineral associated organic matter, and which is very essential to give the soil a good structure. And you know, when you have good structure, it could have better porosity, like mesopores, for example. So in this way, it could also affect on the water retention in soil.
First, congratulations for your presentation.
Thank you.
And I didn't catch up. Why did you see highest level of bulk density in soil under cover crops in compared to the manure?
Yeah, interesting question, and I'd like to share some experience to answer this question. When I collected soil sample from the cover crop plots, it was really hard to me to go deeper into the soil to get soil pores. And as you know, cover crop, it's a living body and it has roots in soil. And as we used different kind of cover crops, like perennial rye, annual rye, red fusky, bluegrass, the root structure is dynamic in soil. And I would say it could be the reason to get the higher bulk density in soil due to having the network of roots in soil. Yeah. Thank you.
Any other questions?
I thought the microphone was on. Hi, thanks for the talk. Very interesting. During your experiment, did you control for rain, like weather, or you just had a snapshot of all your samples? You sampled the same day after rain event. Did you control for that? Do you have temporal information of that moisture content?
Well, we don't consider the rain event for sampling, but in general, we sampled from our plots in early summer. And as it's a long-term experiment, we always consider same period to get soil samples. Yeah.
Thank you. Let's give another round of applause for our speaker.